Welcome to another episode of the Agronomy Highlights podcast. I'm your host, Ryan Spellman, and I am joined with the wonderful co-host, Dwayne Miller. Dwayne, how are you doing?
Hey, I'm doing great, Ryan. Thanks. Hey, we're getting some moderating temperatures this week. If we're recording this here we are, the 18th of December, and we've been entrenched in some cold weather. Yesterday, I think for the first time, we got above 40 degrees locally. We're seeing some snow melt, and we're in for a little bit of rain by the end of the week. So thawing out here in Eastern PA.
It's amazing. I mean, here in central Pennsylvania, we've had snow cover since like mid-November, which I don't remember the last time that's happened, but it's all melting and maybe you can hear it in my voice, but I'm okay with that.
Yeah.
And so I'm thinking about all the things that I can plant here today on December 18th and, manage my nitrogen. Maybe that's a bad idea, but that's where my head's at.
Yeah, I've heard it was the coldest December, the start anyway, in the last 20 years. So we've had some colder weather, but things seem to be moderating. So what do we got on the agenda here today, Ryan?
Yeah, so today we have a pretty exciting episode. We have on Dr. Richard Mulvaney, and he is a professor at the University of Illinois, and he has spent his career focusing on nitrogen management, and the dynamics of nitrogen cycling in a soil, and what that means for how we can manage nitrogen inputs. So he's done a lot of work on organic carbon, on microbial cycling, and I think he has some great messages on the long-term view of nitrogen management. So I think the winter is a great time to have that conversation, to start thinking about our systems. So I'm really excited for this episode. What do you think, Dwayne?
Oh, I think this is going to be a great one. He's going to maybe give us some nuggets to think about in unlocking a lot of this black box theory we have maybe about our soils and some of the nitrogen cycling that's going on. So I'm excited for it too.
Yeah, awesome. Yeah, I think you're right. Like, this might be an episode that folks may come away with more questions that they started, and it's kind of a food for thought episode. And so for you soil nerds and agricultural nerds out there, this will be a great episode to give you all kinds of ideas and thoughts. And so I'm excited. Let's jump into it. So Dr. Mulvaney, thank you for coming on. Why don't you introduce yourself?
I sure will. Thank you, Ryan, for the opportunity to join you guys for this podcast. My background is linked to Illinois. I'm a native Illinoisan. Grew up in the northern part of the state, and my dad actually was an area agronomist for the university for his career. I got an interest in ag, not only from that activity, but also because we were living next to the family farm, and I often was active in farming operations. So I did my undergraduate here at the Illinois and then pursued a master's degree over at Iowa State. And that's really where my interest in nitrogen got its start. I worked under a very well-known professor named Jack Brimner, and he was a world authority on nitrogen. And I learned a whole lot from him and came back here to Illinois and worked on a PhD with Toby Kurtz, who was here at the time. And that too was directed toward nitrogen. So it seems I've been tangled with nitrogen since about the 1970s. I can't seem to get away from it. And there's still a lot we don't know, and it needs work. So I'm continuing with those studies and plan to do so as long as I can be active. And I think there's great opportunity to improve the way we manage nitrogen. And I believe that ties directly to the sustainability of crop production. And we need to do some work in that area. So that's kind of a brief background on how I came to be involved in this area of research. I've been here at Illinois since joining the faculty in 1983. So you would think after all this much time, I'd know all the answers, but I still don't. And in fact, I'm just trying to learn to ask the right questions.
Yeah, so maybe part of this is the more, it's kind of that common thing with agricultural science, right? The more you know, the more you realize you don't know, so, in some cases. So I'm curious, you've decided to focus so much on nitrogen, as you said. And what is it about nitrogen that you think that we have a lot of opportunity to do better with? Like, what is it about nitrogen and its cycling that really makes you think, we need to do a better job and we can do a better job here?
Well, the first response to that would be that with nitrogen, we're talking about the nutrient that is number one in the world fertilizer market. Farmers use more of it than any other nutrient, and it has a bigger effect on yields than any other nutrient. And then we come to the soil side of how it behaves, and we run into a lot of complications there because the soil nitrogen cycle is very much a part of what happens to this nutrient. And it's a cycle that is run by and large by the microbes that live in soil. And that leads us to have to deal with issues like weather conditions and variations among soils. For example, when I started my career, I was under the mistaken impression that soil N supply plays a minor role in feeding the crop. I thought that fertilizers were the main source of N, and my focus in my PhD was on trying to better understand N losses through a process called denitrification. So I was focused on trying to minimize the loss of fertilizer nitrogen. But in more recent times, and with the help of several others, including my good colleague Saeed Khan, I came to understand that the soil's N supply is the major source for crop uptake, and that fertilizers, although they can serve an important and valuable function in increasing productivity, they are ultimately a secondary source. They're supplementary to the main source that comes from the soil. That was a major change in my thinking. It took place around the year 2000. Ever since then, I've been pursuing this idea of soil-based nitrogen management.
Yeah, I think that is, contrary to what a lot of folks would believe, that when we feed that crop with nitrogen, we would rely on that fertilizer-based nitrogen source. So I'm trying to think of a phrase that I've heard before, feed the soil, feed the crop. Is that
Yes.
kind of we're
Yes.
looking at here, right?
Correct. And again, it's a microbially driven nitrogen cycle. And one of the things that I had never really appreciated prior to 2000 was that when we fertilize the crop, we're also fertilizing the microbes. And the microbes have an agenda that's maybe different from the one that we have in mind in feeding the crop. And the microbes, because there are so many of them in the soil, on the order of 1 billion to 1 trillion per gram of soil. So we have a lot of active interest in those microbes. And they're going to be doing something with that nitrogen we apply that might not make it readily available to the crop. And that's such an important part of managing nitrogen, is to understand the broader context of how this cycle works and how to keep it running, and yet do what we can to direct it toward our purpose of increasing productivity.
Yeah, so and I think you've already hit on a few, really meaty things that we can talk about today, and that's microbial activity, how N is immobilized or mobilized, what we know, what we don't know. Now, if we can just back up a second and talk a little bit about soil organic carbon, right? So like I know like this is something when I'm thinking about feeding a soil and creating a better soil for the cycling of nitrogen, this comes up a lot. Can you maybe describe what soil organic carbon, when we say that word, what that means and how that kind of fits into this picture of microbial activity and nitrogen storage? Maybe you can kind of start there with that to build this picture.
Well, I wish I could give you an exact definition of soil organic carbon, but I can't. And the reason is that it doesn't exist. We do know that that carbon in soils provides the mainstay reservoir for holding nitrogen. Typically, it'll hold from 90 to 95% of the soil's total nitrogen content. So it's organically dominated. But what is soil organic carbon, which is tied to the other term, soil organic matter? And although it's been studied intensively by so many scientists since the 1700s, we still don't have an exact definition. We know that the organic matter or the organic carbon consists of things like microbial biomass and the stable portion that is much more abundant than the biomass, and that would be the fraction that we sometimes call humus, stable organic matter. We don't really know exactly how that organic matter is formed. There have been a number of theories over many years, but we still don't really have conclusive proof of how it's formed. We do know it contains nitrogen, and the nitrogen there occurs in many different chemical forms, some of which are very stable, others are more decomposable. So that nitrogen in the organic carbon fraction is the key to understanding how soils supply nitrogen for crop uptake. It is the key reservoirs, the reserve storage portion. It comes out of that reservoir through the activities of microorganisms by a process known as mineralization. It produces a mineral form of nitrogen that we call ammonium, and that ammonium is then subject to more microbial uptake or other processes like conversion to nitrate, and then the crop can feed on either ammonium or nitrate. But in so doing, it's competing with the microbes. And as I just said, they have the numbers game down, 1 billion to 1 trillion per gram. So the plant's going to have some stiff competition from the microbe. The microbes will take up some of the ammonium that they have mineralized, and the process that returns it to their biomass we call immobilization. And so the nitrogen is subject to an internal cycling through mineralization and immobilization. And that's really at the center of the soil nitrogen cycle.
Interesting. So what I'm hearing here, so soil organic carbon is like one of the storage mechanisms, right? So there's that's one storage mechanism. The microbes in a way are another storage mechanism between this, mineralization and immobilization kind of spectrum, right? So how do we, as someone who's trying to raise a crop, right? We're understanding that there's a cycle between these two aspects of the organic carbon, the microbial activity. How do we understand how much nitrogen the crop can get, that's accessible to the crop? And if it's not a case that the more soil organic matter we have, the more can be available. Is that kind of what you're saying?
In a general sense, yes, but many factors interact with soil nitrogen supply, and there have been so many attempts to try and find a way to account for soil differences in nitrogen availability. We've tried measuring nitrate, we've done total nitrogen, or we've done fractions of organic nitrogen, and one such is the focus of a test we developed back some 20, 25 years ago called the Illinois Soil Nitrogen Test. It targets a fraction of the organic nitrogen that we found at that time to be particularly related to crop end response to fertilizer. So there have been a lot of parameters looked at over the years, and the big challenge has always been that we don't exactly know what to measure. And it's complicated by weather conditions that affect the activities of the microbes that release the nitrogen from the organic pool. So nitrogen is fraught with challenges, and it's not simple to predict how much N will come from the soil through the growing season. It's a function of many variables. But here I would note the point that I didn't used to understand. I had the view, as I said earlier, that mineralization was a minor process. It made a contribution to feeding the crop, but the fertilizer was the dominant source. Once I began to understand that mineralization is the major source, then I also began to understand that soils differ in their capacities to supply that N through mineralization. And that was a fundamental turning point in my understanding. And it came about with the help of many people, including my colleague Saeed Khan.
So can you talk to us a little bit, Dr. Mulvaney, about the differences in these soils? Here in Pennsylvania, we've got a broad profile of different growing environments, from some very deep productive soils, limestone based, to some very shallow soils that folks have shale based soils that aren't very productive. So how do these soils differ in their ability?
Okay, let me relate how I began to understand that soils do differ in this respect. It came about because of a PhD project that was carried out in the early 90s. And it was not a student of mine, but I was aware of the work and I read the thesis. And the gist of this was from a project that had set out to evaluate the yield-based approach that was at that time widely used throughout the Midwest, where fertilizer N rate for corn was based on expected yield multiplied times a constant factor, which was normally 1.2. So you'd take the bushels per acre of yield goal times 1.2 and then make corrections for things like a previous legume or manuring. And that's how we got our N rates. Well, in this study by the PhD student, it was done at on-farm sites throughout Illinois. And there were 75 of those. And out of the 75, nearly 1/3 showed no statistically significant response to N fertilizer. So what had been done at these 75 sites were N rate studies. They applied different rates spanning up to what would be a normal N rate for corn production based on a yield-based recommendation. And they went down to a 0 rate, unfertilized check. And so for these sites that did not respond to fertilizer N, the yield without fertilizer was effectively the same as with the highest rate of N. It did not change. That started a great deal of concern about why was this? There must be something weird about those non-responsive soils. And that led to a project that my colleague Saeed and I became involved in to analyze responsive versus non-responsive soils from those response trials and try and determine if there's a chemical difference between the two groups. That's how it all started. And along the way, we gained insights into a great deal more than we expected. And from it came this Illinois N test, or ISNT, that is still being used by some sectors for variable rate N. So that's how it got started. Non-responsive and responsive soil.
So I'm curious, the ISNT test, like my understanding is, and I kind of looked into this a little bit, is you're looking at the soil's capacity for what, right? For the ability to create a microbial environment that allows for more mineralization, or like what did you find about, what makes a soil one of those unresponsive soils to N?
Yeah, so what we had done in that early work was some incubation trials as well as chemical fractionations. And that work did reveal that the non-responsive group was producing more N from mineralization. So yes, they were producing more N. And we also found from the chemical characterizations that we did that there was a specific fraction of organic nitrogen that was related to whether or not there had been a response to N fertilizer. And that fraction at the time we called by the common name of amino sugars. Now, the truth is, the amino sugar term is not really an accurate descriptor. The term I like to use now is alkali labile N because we measure this fraction by treating a sample of soil with sodium hydroxide. caustic lye, and that liberates some of the N as gaseous ammonia that we collect and trap and determine through the test after a heating period of some 5 hours. So that's what happened, and that fraction, commonly called amino sugars, proved very useful for distinguishing non-responsive from responsive soils. And that was all published back in about 2001. So that was the beginning of our understanding, but we had a lot more to learn.
So we have this picture now that we're building that, the type of the soil, it really drives some of this responsiveness to nitrogen fertilizer. Now, and what I know about the ISNT test, have you calibrated it to give you a nitrogen based recommendation based on that crop uptake plus the soil? Is that kind of where this work went?
So, okay, there's a number of points here. And one of them is that the calibration work that should be done hasn't really yet been done. The best that we have at this point is to say that this fraction measured by the ISNT can predict whether or not the soil will need fertilizer in order to increase corn yield. But we haven't calibrated the test level to what would be needed in terms of managing the N rate. That's a critically important part of the work that needs to be done to make this fully usable. Back in the early days when we first develop the ISNT, the critical level was between 225 and 235 parts per million. That was the test level below which the soils that we were studying showed fertilizer response, and above that level, there was no response. Now, as the work went forward back in the early 2000s, many more in response trials were done. And an important point that we came to understand was that farming practices had changed considerably between the early 90s and the early 2000s. And in particular, farmers were planting higher populations. There was more corn in the ground. And we found out that we were missing a number of sites in trying to predict whether or not they would need fertilizer in after the response trials had been done and we had the crop data to know whether they did need in. We were finding that we were missing nearly 30% of those responsive sites. So we had a test that gave them a test level above our critical of 225 to 235, and yet they still needed fertilizer. And much of that issue boiled down to those higher planting rates. So farmers were putting more plants in the field, and if you have a higher population, they need more food. It's very simple. So there came about a shift in our test level so that what would have been adequate in the early 90s with a lower population was now inadequate with a higher population in the 2000s. That was the largest factor we identified. And through that experience, we came to understand there's not going to be just one size fits all with the critical test level. There's no way this can work with just one value. It cannot happen. We're talking about the most bioactive nutrient there is. It depends on many other factors, and one of those is planting rate. So it became obvious that there was this relation between planting rate or population and N supply that would have to be factored into making recommendations with the ISNT. That remains the case to this day.
Are there other management considerations or practices that folks have done or changed over time that may influence that as well? Like one of them I'm thinking about is no-till. If folks are utilizing more no-till now than they have in the past, does that come into play?
It very well could, because we need to consider where the soil is sampled versus where the crop is feeding. And so the ISNT was developed with a 12-inch sampling depth because that's just what we had in the way of samples. That's what we had. So we're sampling just the surface horizon, typically, and yet the crop is rooting considerably below that. And there is nitrogen down below, maybe not as much as in the plow layer, but there's nitrogen down there, and the crop is responding to that nitrogen through part of its uptake. So here's the point. If we confine our sampling to the surface layer and there's not much in the basement, it's going to put more pressure on the surface when we try to calibrate the test. Now, no-till concentrates nutrients at the surface more so than something like conventional till or chisel. And that's going to have an effect on how we test and how we interpret the test data. We do need to keep in mind tillage systems, yes. And we need to keep in mind crop rotation. We came up with evidence that continuous corn would need a higher critical range than corn soybean because there's more input of residue carbon. And here's a point that I need to make. Carbon and nitrogen are inextricably linked. The cycling of one affects the cycling of the other. We probably heard about things like carbon to nitrogen ratios, and having a lower ratio means that nitrogen is more available when the residue decomposes. But maybe what you haven't come to realize or haven't thought about, as I didn't think much about at one time, was why that linkage is so tight. And it's because that the microbes that mineralize in and run most of the nitrogen cycle are heterotrophic, just like we are. They need organic carbon that they burn to make energy, as well as utilizing it as a source of biomass carbon. Now, every one of the enzymes they use to burn carbon contains nitrogen. All enzymes contain nitrogen. And that's why there's such a close link between nitrogen and carbon in the cycling of both elements on this planet. So that becomes a critical issue, residue management and cropping system. So carbon dynamics affect nitrogen availability. And we came to realize that as another of those confounding factors that affects how we interpret the ISNT.
Yeah, that's a very interesting point, and it's something that drives, like, I can see from your situation too, like, it drives so many more questions, right? Of, okay, so if we know that carbon, nitrogen are very much linked, and the microbes that are mineralizing nitrogen are also rely very heavily on carbon as well, I'm curious, how does the dynamics of adding nitrogen to a system that has high residue, right? So it has this high level of maybe microbial activity and mineralization, but immobilization as well. How does, like, adding nitrogen to that system affect the system, right? In the way that we think about it, we say, okay, because we have all these dynamics that might be tying up nitrogen, we want to add more, make sure we're adding supplementary and organic form nitrogen for a crop. But can't the microbes use that too and immobilize more of it? Like, how does that work? I don't know how to ask this, but that's my best stab at this.
Yeah, you've opened a really important issue here, and it's one that I'm still learning about, but I've gained a lot more understanding than I once had. So one of the factors that comes up here is the microbial cycling, and it's related to the fate of residues and the maintenance of soil organic matter. So for in my earlier years before I knew better, I was trained that nitrogen fertilizers had no lasting effect on organic matter. And the message there was that, well, the nitrogen fertilizer might increase residue decomposition early in the cycle. But over the long run, it comes out to be about the same with or without fertilizer. Well, I had to learn a few things on that subject. And my teacher was the Morrow Plots, which is now the oldest continuous experimental site in North America. We've taken that honor from the site that you guys once had at Penn State called the Jordan plots. Jordan plots were originally the oldest site in North America, but as I understand it, a dorm was built on the Jordan plots and you lost them.
Leave it to the university system.
So here in Illinois, the Morrill plots have been active since 1876. And one of the great things that my former advisor, Toby Kurtz, did was to get declared the Morrill plots to be designated as a National Historic Landmark. And so that land that is now the Morrill plots cannot be used for any other purpose. And that's why we still have the Morrill plots. Well, you know, it's interesting. Soils become a record of their management. We another point relevant to Illinois is that in the building that originally housed the College of Agriculture on our central quad, there's an inscription, and it's written in stone, so it can't be erased. And it says that the wealth of Illinois is in her soil. Well, that is absolutely true. But the Morrill plots bears witness that we've lost a lot of the wealth. We've lost it through our management. And here we come back to the point that fertilizer nitrogen affects carbon dynamics and residue decomposition. So we got involved in a project that my colleague Saeed had initiated because he had noticed, walking by the Morrill plots over the years, that in the years when the Morrill plots were all under continuous corn, we're all under corn. And let me tell you here that the Morrill plots are under 3 rotations. Continuous corn is one, corn soybean is another, and corn oats alfalfa hay is the third. And Saeed had noticed that in years when all 3 rotations were growing corn, he would notice that the corn didn't look as good where it was being grown continuously. And it looked the best under corn oats hay. Now he found that interesting because fertilizer nitrogen is applied in largest amounts to continuous corn. It gets it every year. But corn oats hay effectively gets it about 1 out of 3 years. And in the Morrill plots, the fertilizer N rates are the same whenever corn is grown. Back then and now today, it's 200 pounds per acre. So we began to wonder, why would it be that the soil that got 200 pounds every year is lower in yield than when corn is grown in rotation with oats and alfalfa? And that led us to some new understandings that turn out to be documented in the literature in papers that I had never heard of. What we found is that we did a thorough study on the input of residue carbon and on soil carbon storage before and after a 51-year period that began in 1955 with the introduction of commercial nitrogen to the Morrill plots in some subplots. It turned out that, of course, commercial fertilizer had drastically increased yield. But when I went and analyzed the soil and compared the test levels in 2005 to archived samples collected in 1955, lo and behold, I found out that the soil had lost organic carbon. It had grown higher yields for many years, but it did not gain organic carbon. It lost. That was a major revelation to me personally, because I'd always been told and understood, or thought I understood, that nitrogen fertilizers build soil organic matter by increasing the input of residues. And there was a whole lot more residues going in to the NPK treatment than to the subplot right next door that was the check, unfertilized. In fact, the unfertilized had more organic carbon than the fertilized. That was amazing to me. Then we began to scour the literature to find out whether this had been seen elsewhere. We did a global search, and we came to realize that it's very common indeed that fertilized treatments, especially in cereal crops like corn or wheat, they don't build soil organic matter with nitrogen fertilizers. And in fact, we came across a paper published by a guy at Penn State in 1927. This was a guy named White. And here's a sentence from his paper. Liberal use of mineral nitrogen as measured by long-time field experiments, he's talking about the Jordan plots, has stimulated the decay of organic matter in excess of such action by mineral fertilizer without nitrogen. There it is. He'd seen a loss of organic matter on the fertilized treatment. And then we came across another paper from Missouri by William Albrecht. He was working at Sanborn Field. And here's a sentence from his, published in 1938. The lowest supply of organic matter after 50 years occurs in plot number 2 under continuous wheat, given heavy additions of commercial fertilizer. The carbon supply of the soil has been extensively burned out. That's in his paper. I'd never heard of that paper. I never heard of White's paper. And there are others out there that convey the same kind of message. So we began to understand the moral plots is not unique. It's interesting. It's very interesting to me. Albrecht was a graduate of Illinois. He actually got 4 degrees at Illinois. He spent his career at Missouri. And in 1938, he published 2 articles on this topic. One of them is with the sentence I just read you, that the carbon was burned out. The other one came before that paper. It was in the USDA Yearbook of Agriculture, 1938. And in there, Albrecht is giving the message that you need to apply enough nitrogen to build organic matter because organic matter contains nitrogen. It's like baking a cake. You need enough ingredients. But after he went to Sanborn Field and compared carbon levels for those different treatments with archival samples taken years earlier, he came to realize that nitrogen was burning carbon, not building it. And he never again made a statement that nitrogen builds carbon. Never.
That's really interesting. And it's fascinating that I love that Penn State connection. So thank you for that. That sometimes in science we are relearning things that were once known but never picked up and continued. And sometimes it's like this cycle, right? We're talking a lot about cycles, but so where does that, so what I'm hearing here, I don't know many people around me at least that aren't applying nitrogen fertilizer on their corn fairly regularly, right? And part of that is, so I'm curious, where does that leave us, right? So if I'm reducing my organic carbon over time, it would stand to reason that at some point, like if just by applying nitrogen fertilizer, I'm completely stripping the carbon away from the system, and then I need that nitrogen fertilizer. Is that kind of what you're getting at here? That like we've created almost a system where it relies on artificial inputs, and maybe that means, and regardless, our yields are going to go higher because we're injecting that system. But then it's relying on that injection. Is that kind of where you're getting there? And maybe our yields are inflated? I don't know if I'm like being too deductive here, but like, is that kind of where this is going?
You're exactly on line with the message, one of the messages I give in my fertility class. We have put the soil on a regimen of making it dependent on an external input of a critical nutrient. But by doing that, over the long run, we are weakening the soil to supply its own nitrogen. Yes, that's exactly what I'm talking about. Said and I were at a meeting in the Netherlands one time, and a guy came up to us from Africa after we talked about this effect of nitrogen on organic matter. And he found it very interesting because they had the experience that they had to increase their nitrogen rates to maintain yield. The same thing I understand has happened in India. They had to increase the dose just to stay even on yield. It's because the soil is getting weaker. And that has some pretty profound ramifications for the long-term sustainability of how we farm.
It's incredible to start thinking about it that way. And, you talked about the long-term degrading of soil organic carbon. Are there some things or practices that we should be thinking about to start to try to build that back up over time again?
Yes, we do need to think in that direction. So, as I told you, the inscription at Illinois is "The wealth of Illinois is in her soil." While we've squandered the wealth, we don't have as much as we once had. What can we do to make it better? Well, I'm thinking of another published source that I cite in my class from Sir Albert Howard in his book, The Soil and Health. He relates in there the very same observation that we had made from the moral plots and people like White and Elbrecht had made from their areas. And he had been in charge of a network of experiment stations in India for his career. And he made the statement in his book that if synthetic end fertilizers ever come into common use in India, it will destroy the soil. It's right in the book. And he understood that it was because it would stimulate the microbes to burn more carbon. And he says so in some words. So, yes, there is an understanding, and it's been around for some time. Howard made the comment in his book that agriculture will never be sustainable until the animals come back to the farm. That's what he said. And that integrated animal crop production system goes a long way toward addressing this issue with a long-term carbon depletion in our soil. Is it feasible? I don't know the answer to that. I'm not qualified to say. It's an intimidating prospect to try and think of changing the agricultural system that's now in place. I can't say that that's going to happen, but we need to think about options we might have for reducing the intensity of end fertilizer use while substituting other sources like from legumes, legume fixation. And so this brings up other topics that are relevant to sustainable ag. And for this in Illinois, I go back and I share this with my classes as well. I go back to a time around 100 years ago when there was a guy at Illinois named Cyril Hopkins. Hopkins was working on building the Illinois system of permanent agriculture. That's what it was called. And that system was based on three foundations. The first was the use of forage legumes to fix into and feed corn that would follow the forage legume. That was his nitrogen fertilizer source. The second input was limestone. He needed limestone to make the soil more suitable for growing those forage legumes. And third was rock phosphate, because back at that time, phosphorus was commonly deficient in many Illinois soils. So legumes, limestone, and rock phosphate, those were the foundations upon which he built his system. And there's a lot of stories that come from that. He became very well known for this globally. And I can also relate briefly a story about him demonstrating that system of permanent fertility on his own farm. Hopkins went looking for the worst ground in Illinois intentionally. He found it in southern Illinois near a town called Salem. And he bought the land. He dubbed it Poor Land Farm because the only thing it would grow was poverty and mortgages. That's all it would do. And he was determined to demonstrate that this permanent fertility system could make the land more productive. So he applied it in his own farm, and 10 years later, they published an experiment station circular entitled Bread from stones. The stones are limestone and rock phosphate, and he had tripled wheat yields on his own farm over that 10-year period. It earned him a lot of recognition.
So now, like you said, now we're branching into something else that gives me a bunch more questions. And so part one of this, you kind of mentioned integration of livestock and also forage legumes as better ways to maybe increase nitrogen supply in the soil and maintain carbon. I'm thinking, in my experience, where I am in the center of Pennsylvania, we have a lot of dairies, and they are and more, they're maybe moving away from alfalfa, but it is a pretty common rotation to have alfalfa followed by corn. Um, and then maybe it's, 2 years of corn or so, maybe soybeans in there, different systems, for different folks. Maybe there's wheat in between some of their corn croppings, but basically alfalfa for 3 years and a few years of corn, wheat, soybean, something else, mostly corn, right? And then manure is a big input of their nitrogen, Is that like what you're saying? Like, is that a sustainable system, or is that integration of livestock go beyond just, spreading manure?
Yeah, the manure is an important aspect of making a system that's more sustainable. Yes.
Okay.
That's been one of the problems, that we've gone away from the animal inputs towards synthetic fertilizer in. And farmers, at least many of them, they can't afford to lose yield. And this is the case especially with farmers who are cash renting their land. 1 year with bad yield could be the last year. So they can't afford to lose yield, and they've been conditioned to think of synthetic N fertilizers as a form of insurance against yield loss. And so rates tend to be excessive, higher than they needed to be, because the farmer doesn't run out of N. That's a very common problem. So if we can go back to using manure as a nutrient source and replacing some of the fertilizer that's applied, that is going to help us toward making the system more sustainable. Now, I understand that there are a lot of challenges connected with increasing the animal side of agriculture. And here I would just note that back in Hopkins' day, in the first couple decades of the 20th century, agriculture was very, very different from what it is today. You had family farms and you had animal power. So the animals were integrated into the cropping system by necessity. Now we don't have that. And so a huge issue here is, if we're going to bring the animals back to the farm, how do we make it economically possible? What's the market for what we're producing? That's a huge issue that we face.
I agree. We think about our farm at home and go back 2 generations. There were a couple cows there. There were a couple chickens there. There was some horses there to provide that power for the pre-tractor era. And now, we're just cash grain and a little bit of hay in rotation. So that whole dynamic has changed. And if we bring back the use of manure as a fertilizer source, we've got that, those environmental concerns of applying manure that would provide way too much phosphorus, and the phosphorus management folks don't like to hear that side of things. So there's a lot that needs to be, I think, digested with that as well.
Yeah, I totally agree. Yes.
Yeah, so maybe I think we need to go move towards a close here. So the last question I have for you before we end here is, so if I'm listening to this episode and I'm a farmer, right? And I do apply a lot of, UAN or chemical nitrogen to my corn, and I'm thinking, well, shucks, like what do I do now, right? Am I stripping the organic matter from my soil? I can't just stop using nitrogen fertilizers and all of a sudden economically I'm not going to be feasible next year, right? So do you have any advice for farmers listening to this and taking away, okay, like what do I need to do? Maybe I don't have livestock. I don't know if I can do that. What are some steps people can take maybe to increase the organic matter and move towards using less nitrogen in the future.
Okay, so in the short term, what could be done?
Yeah.
One option that I advocate, although it's not nearly so straightforward as I wish it were, that option would be to reduce or even avoid excessive fertilizer inputs. I know that's problematic. I understand it. The farmer can't afford to run short of N and lose yield. But we need to realize that fertilizer N rates oftentimes are quite a bit higher than they need to be. For example, we became involved in a study that was published back in 2006 looking at N response across Illinois in 102 on-farm trials. From those trials, looking at the crop response data, the actual optimum nitrogen rate on average was 80 pounds per acre. But at that time, with the yield-based 1.2 system, the average recommended N rate was about 60 pounds higher than that on average. Now the sites vary, and that's a hugely important issue. Soils vary in the amount of N they can supply, as I said earlier. I have to think we can do a better job accounting for those differences. The ISNT is directed with that in mind. We're still working on it. We've just developed a simpler protocol for running the test with the idea that it'll be easier to use for variable N rates. That's where things need to go. Variable N rates where a rich soil gets a lower N rate and a poor soil gets a higher N rate. I think that is one of the best options we might have in the short term to reduce the burning effect on the soil.
Yeah, that's a great point, and I think one thing that maybe farmers can do is think about your nitrogen management, think about what you're applying, and do some of your own trialing on your farm. I know farmers locally that have over the course of years really dialed in their nitrogen management by doing some strip trialing and seeing what works, and that can be a way to see where that response is. But you have to be willing to really cut back in some areas and some plots.
So I might add to this the important issue of timing and placement for N management. Those things can make a big difference, but I can relate a series of field studies we did back a few years ago using isotopically labeled nitrogen. And some of those studies were comparing fall applied ammonia to in-season applied UAN using Y drops or subsurface knife injection. The studies were done at some of the same field sites in the same growing season. And I remember when we put out those studies, we were thinking, this is going to be interesting. We're going to show the huge advantage of the in-season treatment to fall applied ammonia. I mean, this was a no-brainer. We've got this figured. Well, when the data all came together, it turns out that the fall was just as good as the in-season for fertilizer uptake efficiency. And what actually dominated the story was the soil. We had different sites in the study, and it was the soil's availability of N that had the most to do with fertilizer uptake efficiency. So if the soil was richer and gave more N, there was less need for the fertilizer and the uptake efficiency was lower, and that was true whether it was fall applied ammonia or in-season UAN. It didn't matter. It's the soil that ran the story.
So it all comes back to, understanding our soils, trying to unlock that black box, if you will, of the mystery of soil for us.
Yes. It's such a complex system. Yes.
Yeah, I feel like, man, yeah, with that, I'm right back where I started, but that's okay. That's okay, right? That's part of this. Is there's a lot to know. There's a lot that we don't know, and there's a lot of experimentation to be done. So I appreciate you, Dr. Mulvaney, for coming on and sharing us this really story of soils and nitrogen. And hopefully our listeners can really listen to this and kind of start to think about nitrogen in their own system. And just become aware of the soil, the microbes in your system, feeding that soil, and be observant. So, um,
Yeah, I would just add to that maybe farmers can begin to shake the idea that more is better when it comes to putting on N fertilizer. That would be a good start toward cutting back and making things that are better for managing and stewarding the soil resource.
yeah, that's great. And I think in the fertilizers are only getting more expensive right now, so that is a welcome message for a lot of folks. I do believe. So, I think that that's a great message, and one that if I think we talk about it all the time now with folks. Where can you cut, right? Where can you reduce? And I'm hopeful that we can move more in that direction. And I think it'll take time. Uh,
Yep, I agree.
All right, Dr. Mulvaney, I want to thank you once again for joining us on the Agronomy Highlights podcast. You've given us a tremendous amount to think about. We understand this is not something we can solve, right here, right now. This is stuff that you've been working on for quite some time. And like you mentioned, you haven't quite figured it out just yet, but definitely things for us to think about. So thanks for joining us, and thank you for listening, and we'll catch you next time on the Agronomy Highlights.